I will speak about SIS junction as microwave single photon counter for axion search. Here you can see co-authors of this work. And actually, Leonid Sergeyevich in his talk had already told a lot the principle of operation of such threshold detector, which we are going to use as a single photon counter. And in my talk, I will tell you about investigation of submicron junctions with a tenth of nanoampere critical currents, and using of the phase diffusion regime to get efficient single photon detection. The work was done in a laboratory of superconducting nanoelectronics. This laboratory was created 11 years ago during mega grant of Leonid Sergeyevich Kuzmin, who is a supervisor of our laboratory, and head of laboratory is Anna Gordeeva. And we have experimental and technological equipment. We can fabricate samples. And for example, the sample which was used in experiments with cavity, which have shown Leonid Sergeyevich, was deposited here in our deposition machine. And here we can see photo of our Triton 200 dilution fridge. This is a photo of the sample, sample holder with the sample. And here are two screens, aluminum screen and permalloy screen, which we use in experiments with cavity. And we have measured several JSON junctions. For example, you can see current voltage characteristic of a large JSON junction with critical current of about 8 microamperes. And here is the current voltage characteristic and jump around critical current due to, for example, effect of noise or incoming signal. And we have measured a lifetime for such JSON junction. And it's well known that for large junction, lifetime is very well fitted by the Kramer's formula, which is shown here in this form. And gamma here is a dimensional noise intensity ratio between thermal current and the critical current. And delta U is the potential barrier height. You can see that for large temperatures, about 600 milli-K or 300 milli-K, we have perfect fitting at real temperature, so real value of gamma corresponding to temperature, for example, 0.0293 corresponds to the temperature of 600 milli-K. So no questions with large currents. Kramer's theory work very well. But actually our main task is to find optimal parameters, for example, optimal bias current, to get reliable single photon detection, but at the same time low dark count rate or high dark count time. And actually all estimates were based on this classical theory, all previous estimates. However, we were investigating also submicron junctions with critical current of about 20 nanoamperes. And actually for such small current, it's known that critical current will be suppressed due to MQT. Here, a recent theoretical paper of Golubov, Ilyichov, and Kuzmin in Physical Review Applied. And of course, in SIS junctions, we can have very complex dynamics. First of all, we can have resonant tunneling. Also, in classical regime, we can have a resonant activation effect, which should be taken into account. So we have some optimal frequency close to the plasma frequency, where we will have most reliable detection. Here you can see our recent theoretical work in a classical regime. But also we can have various chaotic regimes, and also we can have phase diffusion regime. And actually one should perform very complex optimizations of the junction parameters to achieve the required sensitivity. When we started measurements with our submicron JSON junction, we have observed at about half of critical current very high escape times. So reaching actually the required limit of 3,000 seconds, about at 10 milli-K, we could see about 4, 5, 6,000 seconds, but surprisingly, even at 300 milli-K, we could reach this limit of about 3,000 seconds. And we understood that Kramer's formula probably doesn't work in this case, because if we substitute gamma, this effective noise intensity corresponding to the temperature, then the escape time will be few nanoseconds or microseconds. And we later have understood that this radical increase of dark count time is due to the phase diffusion regime. Here, the paper where preliminary results were published. We have studied dependence of dark count time as a function of bias current and for various temperatures. And we could see that also there can be good fitting with the Kramer's time, but with efficient noise intensity, with effective noise intensity, much smaller than the real one corresponding to the real temperature. And here are switching current distributions confirming that we are in a phase diffusion regime. You can see that at 800 milli-K we have narrow switching current distribution, and at 320 milli-K we have much broad switching current distribution. Here is again blue is the standard deviation, the width of our distribution, and red is the mean switching current, which we extracted from our histograms. The phase diffusion regime was studied before in many papers. I think one of the first paper was by Martinez, also a group of Ustinov, a group of Peccola, Italian colleagues who studied this phase diffusion regime in various types of JSON junctions. And actually, the phase diffusion regime is multiple phase slips before a JSON junction switches finally to the resistive state. And in our recent paper, which will be submitted to a journal in about 2 days, we have compared for the temperature 300 milli-K the experimental results, this blue curve, and results of direct computer simulations, which was done in the frame of resistively capacitively JSON junction model, in the frame of Langevin equation with noise, and we substituted real parameters, normal state resistance, capacitance, and temperature. And you can see that if we count switches by the voltage, when voltage becomes above a certain threshold, so junction switch to the resistive state, then we can see overlap. Actually, we can see perfect agreement between direct computer simulations and experiment, which confirms that we are in phase diffusion regime. If we, however, make a comparison with Kramer's theory and with the same computer simulation regime, here Kramer's theory is a green diamonds, and computer simulation with escape of phase from the main potential minimum. But escape of phase doesn't mean that our junction switched to the resistive state. It can relax to the adjacent potential minimum and again switch across the barrier and relax in the next one until it finally switched to the resistive state. So we can see several order of magnitude difference between Kramer's theory and simulations with a phase escape in comparison with the voltage escape. Therefore, in the phase diffusion regime, we can get several orders of magnitude from 4 to 7 orders of magnitude difference in a dark count time, which is important for single photon counters based on submicron junctions. Of course, due to phase diffusion regime, we will have less efficient single photon detection, just also because of this phase diffusion regime. And our main goal is to find a certain compromise when at rather small critical current, we will have reliable single photon detection and also rather large dark count time. We have performed single photon detection with a strongly attenuated harmonic signal. Actually, the problem of tests of a single photon counter is the absence of microwave single photon sources. So, as was used in earlier works of Grigory Goltzman and co-authors, we applied the same procedure. We used a strongly attenuated harmonic signal, which decouples to a series of photons, which has Poissonian distribution. And the advantage of a SIS junction as single photon counter is the possibility to calibrate in situ the signal which is received by the junction. And using, so you can see current voltage characteristic at rather high power supplied to the junction. At higher powers, you can see Shapiro steps. And at low powers, you can see photon assistant tunneling steps. And actually, we supply such a power rather weak that we can observe photon assistant tunneling step. We calibrate the power, and after that, we attenuate further power by 1 or 2 orders of magnitude and transfer to single photon regime to very low photon flux. And we do it in the same manner as was done in this similar paper of Professor Goltzman. And but it was done for infrared photons at 4K, actually 4 orders of magnitude in comparison with our energies. And here we can see if we are more close to the critical current, then energy of single photons enough to make switch, and we can see the tilt corresponding to single photon detection. This is 1 order of probability for 1 order of power. And if we decrease bias current, then single photon energy is not enough to make switch, and then 2 photons can make this switch, and the tilt changes, which corresponds to 1 order of power to 2 order of probability. And in our recent paper, we observed quantization of probability tails corresponding to few photon detection. But that time, we still didn't know how many photons we detect, 5 or 10, because we didn't make proper calibrations. Recently, we performed certain calibrations using photon assistant tunneling steps. And here I can demonstrate you N-photon response to 10 gigahertz signal. We can detect even single photons, but at that time, with a rather low quantum efficiency, about 2%. And you can see this floor of dark counts is very near the 100% detection. And here, 2 photon detection, also 2 photon detection for different bias current, 3 photon detection, 4 and 5 photon detection. For 5 photon detection regime, we at that time had dark count time of about 10 seconds, which was rather good result. Now we improved our experimental setup, And we now have a duck count flow 1 order of magnitude less, and correspondingly we can detect single photons with dark count time of few seconds, but the results are not yet published and not yet even prepared for publication. And the results of yesterday night, which we didn't have time to prepare to the talk of Leonid Sergeyevich, I can actually show you at this photo. I think not. The thermometer is located, it's not seen due to the cavity. It's somewhere nearby. This you can see mixing chamber. You can see my pointer. And a cavity is nearby the mixing chamber, and thermometer is here nearby also the mixing chamber and the cavity. And here our sample. And another sample which was decoupled from cavity was in a different sample holder. It was located from another side of the plate, behind the plate, nearly very close to this main sample, which is at the top of the plate. And here, this main result of yesterday night is a rather precise measurement of the cavity resonance, which is close to 14 gigahertz. It's actually maximum at 13.969 about. Here is 0.968. And so these are plots shown by Leonid Sergeyevich. So thank you for your attention. This work was supported by the Russian Science Foundation.
Professor Pankratov, thank you very much for beautiful presentation. Now, please, the question and comments. If I understand, you have the aluminum junction, yes?
Yes, we have aluminum junction.
Professor Claudio Gatti, please.
Thank you, Mikhail. I have a question about your in the setup where you calibrate with the photon-assisted tunneling. How is the device connected to the transmission line? How do you send the microwave power to the junction?
We have two different setups. One is shown here at this photo, and we can supply signal to the cavity from another end. We have two SMR connectors. One is normally loaded by 50 ohm load, but we can replace it by say 10 dB attenuator and connect it to another SMI cable and supply signal to the cavity and get signal. This is namely the way how we measured this resonant frequency of the cavity using the same photon assisted tunneling steps. Another setup, previous one, is when we don't have any coplanar antenna. We don't have any antenna at all. We have several Jerusalem junctions at the sample holder, and we have loop antenna nearby, and we supply signal, and we have a decoupling between antenna loop and our junction by about 6 orders of magnitude. We checked it in our computer simulations. And then we decrease very strongly problems with noise coming from environment, from room temperature. We don't have coaxial cables in our cryostat yet. We use only twisted pairs, and we supply 10 gigahertz signal using twisted pair, and we have about 30 dB attenuation by these twisted pairs.
So, but in this second case, the junction is strongly decoupled from the transmission line, if I understand.
Yes, yes.
So it's a completely different system.
Yes.
Okay.
But we observe the same photon-assisted tunneling steps and we use very the same calibration.
Yeah, but I was thinking that the relaxation time of the junction should be much higher, no? Because you are decoupled from the system. While if you see a 50 ohm line, you can relax on that line, and you have that kind of
no, I think it's more or less the same, because plasma frequency of JSON junction is about 10 gigahertz, and it has very fast on times, and the main relaxation time when we bias back our junction after the switching. It's due to plasma oscillations. But when we use submicron junctions, we have quality factor of order 5 or 3 or 10 maximum, and then we have rather suppressed plasma oscillations.
Now, what I'm saying is, when you connect the junction to a transmission line, the junction sees a parallel 50 ohm. Okay.
Yes, it is.
So it could be, you can think it as a high dissipative system.
Yes, sure.
While in the other case, you have an isolated junction, and you have your junction resistance in parallel, which is, I don't know, 10 kilo ohm or 100 kilo ohm. Okay. So it's a really non-dissipative system.
It's about from 200 ohms to 1 kilo ohm. Normal resistance.
The normal resistance or the subgap?
Normal.
No, but when you are, that's when it's normal, which is supposed to be different. Okay, thanks.
Okay, another question, please. Comments?
There is one question on the chart.
Please.
What is the quality factor of the cavity you have shown?
It depends on the measurements. From this plot, we could extract a quality factor about 10,000. But when we performed these measurements, we replaced 50 ohm load by attenuator, so probably cavity is not optimally loaded, and we expected quality factor by a factor of few higher than we measured just yesterday night. So, but yes.
Excuse me.
Professor Ivanov.
Thank you very much for your nice talk. Some comment. I'm not professor yet, so I'm young scientist. Thank you. My question is following. So the cavity, what you mentioned here, it's coupled to the quad lambda resonator. Is it correct or not in your chain?
It can be different reason. I think lambda over half resonator.
Oh, okay.
Depends.
So, all right. Okay. Thank you. Okay.
Another question? Okay, Professor Pankratov, thank you very much for your nice presentation. So we are arriving at to the end of this very nice section. Thank you very much for all speakers, for all participants of the section, for the very nice